Okay, so time for a flashback. Let's have a podcast over equilibrium. Just kind of the first part of it, and then we can jump into actually doing more practice and looking at some of the math, because this is more some of the concepts behind it. So we did a little activity with straws, and hopefully, ideally, you were starting to see the concept of equilibrium, because it's something we didn't talk ever about in pre-AP. In pre-AP, it was always products becomes reactants, end of story. Now we have to realize that at the same time, reactants might be turning around and making products, and it gets a balance. And that's what equilibrium is. It's not equal amounts of the products and reactants, it's the rate that the products and reactants have been produced is equal. So you can have different amounts of products and different amounts of reactants, and it's at equilibrium. So take the equilibrium out of your brain to say that it equals products and reactants. Rates are what became equal. So let's look at two different graphs. So in your notes, big thing here is look at the difference. I'm going to show you two graphs. Look at the difference on the y. This is the concentration versus time. This is like what you were graphing today with the straws. Now some of you may have had, so look at this is saying, again, reactants are the green, products. So at the end you had more reactants than products, more products than reactants, and you had in this case a lot more, so this would be like the big straw was on the product side. Okay, see this line right here? That shows up on test because it asks where has equilibrium been reached. I can promise you this is going to be an answer choice. So it's not where they are equal, it's where the flat line that the two rates. And remember it's dynamic, you still have them products becoming reactants, reactants becoming products, but the rate of change has balanced out. So this is looking at concentration versus time. Okay, look at this one. This is where the rates, so this time it's rates, and so that's why it is on a single line, is because again this is where the rate has balanced out and the forward rate is equal to the reverse rate. Doesn't mean the amounts are the same, just the rate of change is now equal. So that's the two most common ways you're going to see the graphs, one of rates and one of concentrations. Our graphs we made in the little straw activity was of concentrations. Okay, this is the law of mass action. Really what you're going to see on the test. Write the equilibrium expression. This is typically a point for doing this. So when it says write the equilibrium expression, this is what you're writing. So a couple things that to me should be, that's Panda, that says, you know this, but I don't assume anymore. Okay, remember reactants are on the left side of the arrow, products, so it's always, always, always products over reactants. And coefficients become exponents. So this is where it's different than in kinetics, because kinetics you couldn't use the balanced equation. For equilibrium expressions you have to use the balanced equation. They're both K's, and again this is a large K, capital K. Now what we're going to do is spend a lot of times looking at different types of K's, but it's always products over reactants. That will not not change. Reminder, brackets means concentration. So if you have a Kc, you're talking about an equilibrium constant that is using concentration, hence the C. Sometimes it will just be K or K equilibrium. So that's our more general K. It's just saying use your concentrations, and it's the concentration of products, always reactants. Okay, important thing. Only, and we'll bring this up again a little later in the notes, only use aqueous or gases. Only. So no solids, no liquids, no gases. 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 So no solids, no or that's supposed to be, sorry, that's Panda. If I don't pet her, she barks. No solids or liquids. Please, 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 please put that in your brain, because this can be an easy point just to say write the equilibrium expression, but you have to make sure you have products over reactants. You're only using aqueous and gas. So look at this example. First thing we check, okay, gas, 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 gas. Okay, I'm going to use all those. Then when it says write the equilibrium expression, products, NO2, exponents, exponent becomes coefficient, let's backwards that, coefficient becomes exponent, and then water, coefficient becomes exponent. These can get some crazy math, so you're going to make sure to not lose a square or a tripled or a something. Now look at this could be crazy units, so you know what? We won't have to use any units. Key word here, you can only calculate an equilibrium constant if you have equilibrium concentrations. So you also have to look for those words when you're reading a question. Did they give you initial concentrations, or did they give you equilibrium concentrations? And when we start doing the math next time, we'll look at the difference of how you have to work those types of problems. So again, it's just kind of, what does this K tell me? One thing, K does not change unless you change temperature. And we can't always say it's going to make the K get bigger, because it matters if we have an endothermic or exothermic reaction. So we will look more at that when we kind of look at Le Chatelier and saying how does it change a reaction, how will it change equilibrium, but that's going to be another lesson. Just know that K stays constant unless you change the temperature. So that's another thing when you're reading a problem. Are they playing with the temperature or not? Because they might ask you, how would this affect the K? But if it doesn't change the temperature, it's not going to change the K. Well, we have some shortcuts. These are some nice things we can kind of help if we remember the shortcuts. So look at what we did. I reversed my initial reaction that I had up above. Well, so products became reactants and reactants became products. You could recalculate this whole thing and just do the same thing, plug in your products and plug in your reactants and do the math longhand, absolutely. Or you can recognize and remember a shortcut and go, wait a second, I just reversed it, here's your shortcut. If you reverse the reaction, it's just the inverse of your initial K. Well, I haven't made these for a while, can't draw a straight line. So reverse reactions, it's the inverse of your original K. Looking at a couple tests ago, these popped up more than once, that if you remembered some of these shortcuts, it could get you a multiple choice question. Okay, let's go to another kind of shortcut. What if you multiplied? Now, when this would come up, it's kind of like Hess's law, if you remember Hess's law. When we added our reactions together, and we ended up with an overall new equation. Well, sometimes you might have to multiply the equation, kind of even like what we did. Think of when we added equations together for redox reactions. So you can do the same thing with all types of reactions. So if you have an equilibrium reaction that you're adding together and you need to multiply everything, that shortcut, look at here, if you multiplied the whole equation by, let's say, 2, that's consistently taking 2 to all of your coefficients. Again, look at the shortcut. So you could take all these new numbers, plug them into your K expression, plug them into your calculator, or you can recognize, what did you do? What's consistent? It's that coefficient raised to the coefficient. So whatever you multiplied this reaction by becomes an exponent. Again, this is all of your original K. Okay, well, what if we add those reactions? Again, think of redox and how we added reactions together to cancel out the electrons. We've added reactions together to make sure it adds up to an overall mechanism. So sometimes we add reactions together. If it's an equilibrium reaction we're adding together, then you are going, and they have two separate K's, then what you'll end up doing is multiplying each of the K's to get a new K. So that's all that this is saying. This is the K from reaction 1 that you added to reaction 2. So it ended up with this new K that is just multiplied of the originals. Here's the nice thing. Yay! You get to have a naked number. It feels a little weird after all the times I've told you, what's your units, what's your units? Big K, no units. Little k, units. So for the next, while, probably next month and a half, we're going to do a lot of Ks. K doesn't need a unit. Concentration still gets a unit. And you might have other things saying how many moles are left, how many grams is left, what is the pressure. Those will need units. K does not need the units. Okay, so, see, and then I say okay. This to me sometimes is like, duh, but let's not get the duh. It's equilibrium only if I use equilibrium. You can only call it an equilibrium constant if you know the numbers you're putting in are the concentrations of your reactants and your products at equilibrium, not at your initial. That's going to be something called Q. And sometimes we will have to calculate Q and compare Q to K. But that's going to be the next day that we're going to do that. So right now, just know you can only calculate an equilibrium constant if you have equilibrium numbers. So look at these differences. This is just showing some examples. You had all different initial concentrations. Here's your in equilibrium. First thing we always look for now, you look for that double arrow. Are you looking at an equilibrium problem or are you looking at a straight stoichiometry problem? So this is equilibrium. Well, these were the concentrations that were given. We will figure out how to calculate those later. Now look at this. Even though these are different equilibrium concentrations, their ratios are staying the same for this reaction, and as long as the temperature stayed the same, look what the equilibrium constant did. It stayed the same. Okay, here's another one that hopefully on a quiz you don't cry because you made a silly mistake. We can have KP. P, highlight that, KP. P stands for pressure. Do not use brackets when it's asking for a KP. KP needs partial pressures. So if it says write the KP expression, you write it with partial pressure, but it's still products over reactants. That hasn't changed. You're just going to use the partial pressure. Now, you can use parentheses, but make sure your parentheses do not look like a bracket. What's more important is that you have big P sub. So let's say you wanted to write the equilibrium that this really, let's see, nitrogen gas plus hydrogen going to ammonia. Okay, if it said, what is the KP expression? KP. Okay, partial pressure of ammonia. And when there is an exponent, we usually put it in brackets and it becomes, coefficient becomes exponent, partial pressure of nitrogen times the partial pressure of hydrogen to the third power. That is your KP expression, using partial pressures instead of brackets for concentrations. That can be a point. And again, we only use gases. And in here, everything was a gas, so we didn't have to worry about it. And in the KP expression, it only would be gases because those are the only things that are contributing the pressure. One thing, Look at here. This is why I said I tend to always change things to atmospheres, because in a KP, it has to be in atmospheres. It has to be in atmospheres. It has to be in atmospheres. So if you ever have something in torr or millimeters of mercury, you're going to have to convert it to atmospheres. Okay, so you do have a shortcut. This is not on the formula chart. Not on the formula. It would be one of those times I'm like, there's a few things you may want to know. This is one of those. You may want to put it in your memory bank. KP, it's how can we get, if I have a KC, how can I get to KP? This is the same R, this is in PV equals nRT. Temperature has to be in Kelvin. Okay, this delta N is the change of moles of products. Okay, so let's go back to my favorite reaction. Notice states are going to be a lot more important in this because we have to know if we can use it in the equilibrium expression. Okay, so my delta N in this case, it's products minus reactants. So delta N in this case, I have 2 moles of gas minus I have 3 plus 1, 4 moles of gas on the reactants. So in this case, N would be a minus 2. So the positives and the negatives do matter, and so that's why it's always product minus reactant, because you want to know how much is that pressure going to have effect. Well, look at if you have something that's actually going to produce the same moles of product and the same moles of reactant, that would give you a delta N of 0. So if delta N is 0, this whole value would become 1, and so Kp will equal Kc when you have the same moles of gas on the reactant side and the product side. That actually shows up quite a bit. So if you're going to do this, I would definitely check to make sure, oh wait, are they trying to trick me? And do my moles of gas change? Okay, another thing, we've already said this. Look at this state. Solids and liquids never use. So if you had to write the Kp expression for this, you're only going to use this. Only use your gas. Okay, what the reason is these amounts of your liquids, so water is never going to be in your expression, ever. Ever, ever, ever. And the reason is it's just not significantly changing compared to the other concentrations. So even though there's 4 things in this equation, and this is very, very, very common when we start doing acids and bases, we have water in our equation, but we don't use it in our expression. You're going to have products over reactants. Do not put in solids or liquids. And this is just, it doesn't matter the amounts. We're producing the same amount of the gases. That is what we are looking at when we talk about the Kp or a Kc. Okay, so what does this K tell us? When I look at a K, what is it going to be able to tell me? Well, one thing I know that if I have a really, 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 really big K, use your common sense. Products over reactants. Well, mathematically, if I just look at products over reactants, and this is all equal to K, the only way I'm going to get a large K is if you have more products than reactants. Okay, that makes sense. Well, what if I have a K less than 1? Then you're going to have a small number. That must mean your reactants are really big, because when you divide by a small number, you're going to get, when you divide by a large number, you're going to get a small number. So that means reactants are favored. And that's kind of the wording, which side is favored. So what if you have a K equal to 1? Well, then products and reactants must be equal. That really doesn't happen very often, but it can. K tells me absolutely nothing about speed. This is not kinetics. This is just saying where that reaction lies. So if I have a really, really large K, we kind of have a rule of 3. So if we say it's bigger than to the power of 3 or 1,000, then pretty much we can say it goes to completion. The amount of reactants you have is so small that we really can start treating it like stoichiometry. If we have a really, really small K, then we sometimes get to ignore the product side and say, oh, you know what, you're going to make so few products that we really don't have to worry about them in terms of significant figures. That's why typically most things are in 3 significant figures. That's why the rules of 3, and we will definitely keep revisiting this. So look at the pictures. If it just said, what would K be greater than 1, less than 1, equal 1? That's definitely a very common question. And they give you pictures. Well, HBRs, my products, count. There's a lot more HBR, therefore K is going to be larger than 1. Okay, look at this picture. I only have 2 products. I have a lot more reactants, therefore this K is going to be smaller than 1. Okay, let's just do a few practice there on page 4. Okay, look how we're reading this. They give you an equilibrium expression. A couple things I'm looking for. Gas, gas, gas. Okay, after the system has reached equilibrium, it's given me concentrations at equilibrium, and it wants to calculate just a K. Well, since it's given me concentrations, I know I'm going to be calculating a Kc. Even though they're gases, this with concentration, so you can calculate a Kc or Kp of gases. You can only calculate a Kp for gases. First thing, and this is typically always going to be question A, or like I. Write the equilibrium expression. Just write this equilibrium expression. Most of the time this gets you a point. Products over reactants, coefficients become exponents. Then you're going to substitute in the numbers they gave you. Don't forget your squared. Don't forget your exponents. Really, really get comfortable with your calculators. We're going to have to really make sure you're comfortable with scientific notation because we see a lot of small numbers and a lot of big numbers. So, and if you're not comfortable about it, in the next couple weeks, let's make sure that you're talking and we're getting comfortable and you're always using the same calculator you use on test. And then you just plug it in and you chug out your answer. And again, we don't worry about units because big K doesn't have any units. So you've just calculated an equilibrium expression. Okay, now look at how this problem can start changing. So we have our initial. Now it wants me to calculate a K for this reaction. This is where, when you look at it like I, or ABC, remember this is all about the same equation. So you have to say, oh, how is this equation like the other equation, or what did I do? Here's your initial, here's this, what did I do? Oh, I reversed it. So I could recalculate it, absolutely. You could take those same numbers and plug it in. Or you can remember your shortcut that we talked about in the beginning, that the inverse of that is going to be your new K. So just take the inverse of the K you just calculated, thinking if it's really big in one way, if I reverse it, it's going to have to be really small this way. It's going to have to be really big the other way. So this number makes sense. There's going to be a lot of this. Does this number make sense? Does this number make sense? And so yes, that makes sense. Okay, look at this one. What did we do? Well, we didn't reverse it because these are the products in the same way. But look at here. Before this was a 2, now it's a 4. And this was a 2. And this was a 1. Oh, we multiplied this whole reaction by 2. So remember our shortcut for K, when I multiply it by 2, take your initial K and raise it to that exponent. So take your initial K that you calculated up there above on A, raise it to that power. And that's going to be your new K. Okay. Last thing we can manipulate. Well, what if I want to find the Kp for that reaction? We remember our shortcut. Kp is Kc RT delta N. So look at your reaction. I have 2 NOs plus 1 chlorine, so I have 3 moles of gas. So this delta N right here came from your product side that I had 2 NOs and 1 chlorine, so I had 3 moles of products minus You had 2 NOCLs, 2 moles of reactants, so therefore you had a change in moles of gas of 1. That's where that came from. And then this is just R, temperature has to be in Kelvin. So make sure when you do the math though, if this wasn't 1, that it is RT raised to that power. It's not this entire number raised to the power, it's just R times T squared, or R times T to the negative 2. And then you're going to take that and times it by your initial Kc. So do this math first. Doesn't really matter when it's raised to the 1. And so then you end up with the Kp of 3.92 times 10 to the negative 4th. Okay, so I want you trying problems on 5 and 6. So then we can come with questions, and then we're going to get more into the math of it. But definitely try the questions and come asking questions, and that way we can definitely get in and start calculating Q versus K and do some rice tables. Rice, baby. I will see you next class, and have a good weekend. Yeah, weekend.